Okay, here we go. Chapter 14 is beginning. Let me see here. Pay-per-view. And I have my oranges. These are replacing the M&Ms. And so I don't know if I should get one at the end of page one or not, but there are enough, I think. I have water, so I'm ready on water. I don't usually do bottled water, but I got that and didn't drink it all at a conference, and so I refilled it. I have tea. Usually don't keep my tea bag in there, but forgot to take it out. So, chapter 14, is this too close? Kevin set me up, which was really sweet of him. Okay, so chapter 14, that is page one. I think I will have an orange. Remember all those, my UCLA sweatshirt might be too warm now that I'm videoing. And those oranges have a little bit of seeds in them. Maybe I can grow a tree. Okay, let's see here. You remember all those surfaces that we had from chapter 12, the ellipsoid, the elliptic paraboloid, um, the hyperbolic paraboloid, which looks like a saddle, the cone, the the hyperboloid of one sheet, and the hyperboloid of two sheets. It's just hard to even say all of them. There it is. But they're going to come up a little bit here in this section, and so they're just kind of a little reminder of them there on the first page. You can certainly go back and look in your book about them. So 14.1 is starts us off on functions in several variables, so more than one variable that we're going to be looking at. A function of two variables is a rule that assigns to each ordered pair of a real number xy in the set domain a unique number denoted f at xy. The set D is the domain of f, and its range is the set of values that f takes on. That is, and so this will be your range, the values, the outputs of f at xy. And so, and you know how when you were first learning about functions, they told you about f at x, and then they said, hey, that's a secret set way of saying y. This was in 2D. Well, now we have z is a secret way of saying xy, f at xy. And these are the values, x and y are part of your domain, and your range are your z values. And this is a picture right out of your book, I'm sure, that kind of depicts that situation. So this is an element in the domain, xy here, and then there is some height that is associated with, and it's a z value called f at xy. And there are others here. Here's another one, ab, and what it's associated with in there. So z equals f at xy. This has two independent variables, where when we were in two dimensions, oops, this was 2 dimensions, and this was meant to be 3 dimensions. 3 dimensions. But when we were in 2 dimensions, we had just one independent variable, and that independent variable was x. And we had just one dependent variable, and that dependent variable was y. Now that we're looking at this, there are two independent variables, x and y, and one dependent variable, z. And so that's kind of the story on there. The domain will be a subset of R2, and the range is a subset of R. Because remember what each element in the domain look like. They look like X, Y. They're ordered pair. There's two things there, whereas each element in the range looks like a value just Z. And then the graph of the domain. Now you might be thinking, well, we haven't graphed domain before. Well, you probably have. or at least thought about the graph of the domain in 2 dimensions. I'm going to put that up here. I can't help myself but to show you 2 dimensions. If I had y equals the square root of x, and I wanted to graph the domain, well, the domain is x is greater than or equal to 0. And so I would graph that on a number line. So here's 0, and greater than or equal to 0 is this way. And so this is the domain, and that would be a graph of the domain, just a number line. So that's what that would look like in 2 dimensions, right? And so if we graph y equals f of x, if you graph the domain, you just get a number line. And we just did that, just a little example just to kind of show you. And z equals f at xy, the graph of the domain would be in 2 dimensions. And so we've never done that before, but we are going to do that. And then w equals f x y z. That this graph, if you graphed the domain, it would be in 3 dimensions. And that it's more difficult to graph things in 3 dimensions. And then going along with that, if you wanted to graph the function, so this was one independent variable, one dependent variable. But if you wanted to graph the function, you must have 1 dimension more than the number of independent variables. So if I want to graph y equals f of x, when I graph that, that's going to be in 2 dimensions. So if I wanted to graph y equals the square root of x, if I wanted to graph the function, this was a graph of the domain. If I wanted to graph the function, then it would be in 2 dimensions, x, y, and it would look something like that, is what it would look like, right? Y equals the square root of x, and that would be the graph of the function. And so it has 2 dimensions. So that's all they're saying here. So if you're like, oh my gosh, I don't know that. Well, you do. And then z equals f at xy graph. This graph of this function would be in 3 dimensions, and it would be a surface is what it would be. And we did graph some of those in chapter 12. And in fact, all of these things that I was showing you here are all surfaces. The other one that's a surface is a plane. And so all of those are surfaces, but also not shown there is a plane. And then if you wanted to graph this, then it would be graphed in 4 dimensions. And it's hard enough for me to graph 3 dimensions. So it blows my mind to even think about 3 dimensions, 4 dimensions. Okay, and graphing. So now we're going to give a try. Let's see how this works. I don't have it stapled together, so I'm not having as good a luck as I normally have with how I turn things. So this is page 4. And I think I have it kind of zoomed in. I think it is my problem. Or maybe my camera is not in the right spot. I don't know what my situation is, but there's a situation, I'm sure of it. Okay, so this is kind of because we're going to be mainly focusing on things like this as our main focus. And so this is where z is equal to 0. So that's just when z is equal to 0, you just have the xy plane is what you have. Now, a lot of times when we draw it like this, xy, right? And I know that it doesn't look exactly like that, but it's still just this is all that it is, and z is 0. And so when the 2 independent variables x and y, and here z is 0, and then what they map to is a height, and that height is a point on a surface. And there are infinitely many points on that surface. And they create that surfaces. So that's what's kind of going on. So we're going to kind of give a try to that. Some of these surfaces we can recognize and we can graph, and others of them we might not recognize and graph. So this is example 1. They're asking us to find f at 3, 1, the ordered pair 3, 1. And so x is 3 and y is 1. And so you just plug that in there. And so this, if you're trying to find f at 3, 1, I wish I would have just given myself just a little bit more room. I always talking about the room, as you know. I put parentheses when I substitute, always when I'm showing students how to do it, and mostly when I do it on my own as well, even when they're not necessary, because I find people leave them out when they are necessary, and they don't mess you up if you put them in when they are necessary. So that's kind of my story. But here I'll say that, and then I'll make an error, and so I shouldn't be all braggy, and so. F at 3, 2, 3, 1 is 3/2 is what that is equal to. And so this ordered pair maps to that value, which is basically 1.5. Here, they're asking me to state the domain of F. I didn't eat my orange on the last one. Yeah, I have. Lee Kong Lu gave these oranges to me. They're really good. They came off our tree. They have seeds, and each little slice has a little seed. And I'm going to put them, grow a tree of my own with them. Okay. So if you're wanting, I hope that you were thinking about the domain. Well, if you have a fraction, the only thing that's not allowed is for the denominator to be 0. So we want to make sure that x minus y is not equal to 0. So that would be what we would want in order to be good values of x and y. So that would mean that x cannot equal y. And if we wanted to write it a little more formally, we could say the domain equals the set of x ordered pairs, x, y, such that, so this is the set of ordered pairs such that x is not equal to y. And then you end the set. I'm not going to tell you anything more with that set bracket right there. And then something that they ask you to do in the textbook is they ask you to sketch a graph of the domain. And so we will definitely do that. And so since we have two independent variables, we're going to need, in order to graph the domain, we're going to need 2 dimensions. So here's x and here's y. And one thing that I can sketch really easily is x equals y. And so because it's is not equal to y, so, or y equals x. And so do you guys agree with me? Here's y equals x, that line. And so I really want a dotted line here at y equals x, right? And then all other ordered pairs besides those on that line are included. So everything over here, all ordered pairs over here are part of the domain. And all ordered pairs above the line are part of the domain. And so I'm shading and saying that's the domain. The line itself is not part of the domain. So this is the only thing that's left out of the domain, is that line right there. And then I just took and that's why I printed my notes in color, is I just went on whatever that site is where you can graph things in 3D. And I asked it to graph this. So I put in Z instead of F at XY, but that's exactly the same. And so I asked it to graph this. And you can clearly see that the line X equals Y is totally, there's no function in that spot anyway. So I just thought it was kind of interesting. If you go and you graph this on there, then you can move it around. And I guess I could have done that on my computer screen, and that would have been really, really, really good. I don't know if I can do it very easily. So let me see if I can. We'll give it a just a tiny whirl here. Um, I don't know. It might not load. It is going to load. it was acting like it might not load. And I was like, oh, forget it. I'll let you guys do it and give it a try yourself. Okay, now I come back here and I get over here and I go computer screen and then here it is. And I have my mouse, and so I'm not very good at doing it with my finger, but I'm better with moving it around with my mouse. And so I like to GeoGebra, I can't say that right. I know Megan always helps me. And then why can't I manipulate that very well? What is the deal? Why am I not being able to manipulate this? There, I got it finally. And so that you can kind of see. Here is positive X, and here is positive Y. The red is positive X, and the Y is, and they don't always start it off looking like our book does. So I always arrange it to always look like our book because it makes me feel better about it. And because of the right-hand rule, what's positive for X, Y, and Z matters where you put them, right? You got to use your, oh, I'm putting that underneath there, and you can't see me putting that underneath there, but the right-hand rule. But you can clearly see at the line y equals x, there's no there's no the function, the surface is not there, and it kind of makes a weird looking surface, as you can kind of see that one. Anyway, so there's that story, and so I drew it on there. Oh, I'm trying to come back over here and do paper view. No, person view, no, paper view. It is paper view is what I should be doing. Okay, so we looked at that. And so that was page 3. And I usually have these stapled, and I can have another orange. So this one, I hope that you're already looking at it. And so they want us to state the domain. And I know that anything underneath square root has to be positive. And so I'm looking at 4 minus x squared minus y squared. Where'd my minus go? Where'd my eraser go? Is greater than or equal to 0, right? And if I do a little rearranging of things, I have negative x squared minus y squared is less than or equal to negative 4, right? I can take away 4 from both sides. And if I multiply through by a negative 1, which I'm thinking about doing, so if I multiply by negative 1, just to make it look better a little bit, because they're asking me to sketch it, right? So if they're asking me to sketch it, it'd be nice if I knew what it was. And if I multiply by negative 1, don't forget that you have to flip the inequality symbol. So this is going to be x squared plus y squared. Flip the inequality symbol, and then times negative 1 here is 4. And so I hope that you're recognizing what that's going to be. Now I can write this in notation like your book would. The domain equals the set of ordered pairs xy such that we get this circle. And then end a set over there. And so if I want to make a little sketch of this, I need xy, and it's a circle with radius 2. And so I'm going to draw a hair radius 2, radius 2. Oh, that doesn't look very circular, but it is. And everything on the inside of that circle goes greater than or equal to. So this is the domain. Everything that's in the inside of this circle will be mapping to some value and creating a height. Now, we can also say the range on this one. Some of them are hard to say the range on, but this one's not hard to say the range on. And the reason it's not is because if we're looking, I'm going to say z is our range. So if we're looking at z equals the square root. And that means that the very lowest value that z can be is 0. because the square root of any number, the very lowest it could be is 0, 0 or some positive value. And so this starts me when I'm talking about my range. I'm going to say my range equals, and the set of z's such that, and then I know that z is bigger than 0. Now, on this particular problem, I have 4 minus x squared minus y squared. And so this is never, because you're subtracting a positive, could be 0 as well. And so if you look at this, when I subtract something that is, this is minus a positive or 0, so a positive or 0, subtract a positive or 0, 0 or a positive, so that you're thinking about this. And so if I'm wanting the biggest it could possibly be, then that would be when I don't take any away at all. This is not negative. I'm never subtracting a negative and then getting a positive, and so that it gets bigger underneath that square root. So the biggest this could be is when this is 0. And when this is 0 and that is 0, we get the square root of 4, which is 2. So the biggest this can be is 2. And then a little graph of it. And if you're thinking, well, it's going to map things from the XYZ plane up some height, right? Up some height. And what's the tallest it ever is? Well, the lowest it ever goes is 0, and the tallest it ever is 2. And yeah, that's what it's making, is it's making kind of half a sphere. And I won't go and put this one in and manipulate it around, but if you would like to, you definitely can, and look at it from all different angles. If you like, I put the X coming out here and the Z here and the Y here. So I always try to orientate it in that direction. If you're looking at it and you're thinking, well, that's not the equation I thought that there would be for a sphere. Well, it is if I squared both sides, right? So this would be z squared equals 4 minus x squared minus y squared. And then if I added x squared and y squared to the other side, I have x squared plus y squared plus z squared equals 4, right? And so that definitely is a sphere. Now, the reason it's only half a sphere is because of the original equation was only the top half, right? Because z has to be positive. But anyway, so that's kind of that story on that one. We did a lovely job on it. Okay, so then on this next one, example 3 on page 5 here, it's asking us to state the domain. And we have several things that we have to kind of watch out for. We have a natural log here, and the input of a natural log has to be positive. So I know that y minus x has to be greater than 0, not equal to 0, because it's not okay. Put it on your calculator. The natural log is 0, and your calculator will say, nope, can't do it, right? So if I do the natural log of 0, my calculator says no, can't do it. So that happens at x equals y, right? Y equals x. And so when they're equal to 0. Now, the other thing is my denominator down there, it's underneath a square root. So this is an and, it has to meet both conditions. Elements of the domain have to meet both conditions. X minus y plus 1 has to be, now I would normally say greater than or equal to 0, but because it's in the denominator, it can't be 0. So I'm going to say greater than 0 here as well. And so I want to check it out and see about putting these things together and seeing what I have. There's more than one way of writing this, and I just kind of was noticing just now, and I didn't do this earlier, but I'm just noticing just now that I might be able to, because of the way it's written, I might be able to get y minus x on trap between two things, perhaps I can. And I'm thinking about doing that. And so if I rearrange this, minus y plus x, and then I take away 1 to the other side, is greater than -1, like that. And then I wanted to make it y minus x, just like that is. So I'm thinking about multiplying this through by -1. And if I do that, don't forget you have to flip the symbol. So times -1 is y, times -1 is -x. Flip the symbol. Anytime you multiply an inequality by a negative or divide by a negative, you have to flip the symbol. And then times -1 is 1. And then I kind of was noticing, I'm going to rewrite this. This is 0, and I want the alligator to eat the y minus x. And I don't know if you kind of notice what I've done here. I've put these together like that so I can put them together and write it as a compound inequality. This is what I was thinking of doing. And so that's my domain. Can I write it? Do I have enough room here? Domain. And there's more than one way of writing it. And I just noticed that just now. I actually didn't write it like this the last time that I did this problem. And I think that this problem actually came out of your textbook. And I think that my answer before matched, but I just noticed that how clever this was to write it like this this time. And so I think how I wrote it before. So this is definitely an or. You could have written it, the domain. Can you see what I'm writing? I hope you can. I think I wrote it like this. Y is greater than x, and you definitely need the word and not the word or. Y is less than x plus 1. And you can see that what I had done before, I added the x to the other side, and I added the x and the 1 to the other side, and then multiplied through by a negative. Either one of those is good. It's all good on that. So I want to sketch the domain here. And either one of these, from here, if I was going to sketch the domain from here, I think that I probably would have to write it in two pieces. So actually, maybe this, how I did it before, was kind of better because it's easier to sketch the domain from here. So you would graph y equals x, but dotted. So here I am graphing y equals x, but dotted. Has to meet both conditions. And then the values for y that are greater than are that way. And then I want to graph y equals x plus 1. And it's the same slope. These are parallel with one another, right? Here, the boundary is y equals x, and the boundary is y equals x plus 1. And these have the same slope. Of course, you could just pick points and knowing that they're lines 0, 0, and 1, 1. And this one here, gosh, my feet are cold. 0, 1, and 1, 2, right? And so you could plot it knowing they're parallel with one another, and this one crosses the y-axis at 1. I don't know. I teach algebra a lot, and you guys are like, do you have to give us so much advice on how to graph a line? Sorry. Yeah, I probably do. And then this is y is less than, so that's this direction. And so it's just the domain is just this little valley in between is what it is. And then here is a kind of a picture of it. If you wanted to go and look at it and graph it yourself, and on a 3D grapher, and kind of play with it, that would be great. It's not one that I don't think it's one that we would know. This is one that we should know, but the other two, I think we would know them. Too many examples. Sorry. I have sometimes too many examples, and this is one of those times. Okay, but this one is 3 independent variables. And so if I'm going to sketch or describe the domain, I have something that will be the domains in 3 dimensions, right? Because of 3 independent variables. I can't draw, this is in 4 dimensions if I was to draw the function, and so I won't be able to do that. Okay, so what I know that z is not equal to 3 because the denominator cannot be 0. And this up here, 4 minus x squared minus y squared is greater than or equal to 0. And we've already seen that one today, right? Remember, we manipulated it. It's the same one we had. And so I'm going to manipulate this just really quickly. Just remembering, I hope that you guys remember that we just did this one, the same very one. So I've done 2 steps, 3 steps at one time. But it is a circle, right? And the insides of a circle. So our domain are the set of x, y, and z such that z is not equal to 3 and x squared plus y squared is less than or equal to 4. And then if I'm going to draw this, I have to draw it, the domain, in 3 dimensions. And so this is x, this is y, this is z. And this thing right here is a cylinder that's, because z is missing in the equation, a cylinder along, what did I do? I was thinking about my orange and whether or not I had got it on the previous pages. I think that's what I was doing, because I labeled those wrong as I was not thinking, but I was saying along the z-axis, and then I had labeled it y. I don't know. Anyway, so this is a cylinder along the z-axis with radius 2. And so that's what I kind of have going along here, is I have this cylinder along this axis with radius 2, except for where z is equal to 3. So I'm going to come in here, right here, 3, and then there is a missing, at z is 3, there is a missing hunk. So all the rest of this is shaded in, and it goes up and up and up. And I don't know how to show that it goes up and up and up, but here is a missing disc, kind of like a missing disc right there. So I should say all points, I'll describe it, right? All points in the cylinder. Ooh, is that how you spell cylinder? I'm not sure. Maybe AR, maybe ER. I'm not sure. I don't know. Along z axis with radius 2, except at z equals 3. Something along those lines. I don't know. Kind of describes it. Okay, so some of them you can graph the function. I think of the ones that we've looked at so far, that we could graph one of them, and so we're going to try this one here and see if we can graph it. So it says sketch the graph of the function. So the first thing that you want to do is you want to say that, hey, this is z. And then you would like to manipulate it, hopefully, so that you recognize what it is and put it in standard form. And so when I look at this and I get this hint right here, which is really nice, but because I have x to the first, y to the first, and z to the first, I know that, hey, that thing is, that's a plane, is what that is. So this is 2x minus 3y plus z equals 6. And there is my plane in standard form. Now, if I want to draw it, I have the picture over here just so that you can see it better drawn in 3 dimensions than what I can do because uh, because I'm lovely, as you well know. So I'd like to know where it crosses the x-axis, so the x-intercept. How you find the x-intercept is you let y equals z equals 0 is what you do. And so if you do that, the x-intercept is at 3. Is that okay? So the x-intercept is at 3. And in fact, it's an ordered pair, ordered triplet, 3, 0, 0 is what it is. So that's the x-intercept. By the same token, the y-intercept is let x equals z equals 0, and the y-intercept would equal, so these are 0, so we get -2. So the ordered pair 0, -2, 0. And then the z-intercept, so this is how you sketch a plane, is you get the intercepts. And if we put in 0, if we let x equal y equal 0, then this will be the only one that's not 0. So that's 0, that's 0. So we would get the z-intercept to be 6. So this is 0, 0, 6. And so then if I want to sketch this, so this is z, 1, 2, 3, 4, 5, 6. And on x3, 1, 2, 3. And then on y, -2. And then I'm just going to draw this in here. And there's my plane. And so, oh, can't see where I'm drawing it. And so anyway, so my best drawing over here. So here on the 3D grapher, they draw the x y axis, and I left it turned on because I think it is kind of helpful to have that there. And so you can see that this plane is just leaning up against, it looks a little more 3D in their drawing than it does in mine, but actually look, I did a beautiful job. I don't know, anyone think I did a beautiful job there? I think I did. Okay, so this is 5 and 6. And nice. Here they're asking me to sketch the graph here of this one. And so we're going to give a try to sketching the graph of it. So if I want to sketch the graph of it, I would be saying, okay, this is z equals and half and square root of 36 minus 9x squared minus 36y squared. Oh, that was the problem I did in the book. It was 4y squared. So similar. And so if I can move the half over and then square both sides, if you like. Why don't I do that? So if I move the half over, so multiply by 2, we'll get rid of that half. So this would be times 2 on this side, times 2 on that side would make 1. And then if I square both sides, and I'll go back and talk about the domain and the range a little bit on it, but I'm just trying to get a feel for what it is, first of all. And because I square both sides, I know that it's probably only part of, this is only part of what I'm gonna be saying down here. So if I square both sides, 2z squared and then the square root squared, right? So this is 4z squared equals 36 minus 9x squared minus 36y squared. And then adding this stuff over here, 9x squared plus 36y squared plus 4z squared equals 36. And I would know that it's a sphere if the coefficients of x squared, y squared, and z squared were all equal to one another. And so since they're not, I know that it is an ellipsoid, is what it is, an egg. And so because they're not all equal to one another. And the standard form for one of those is to have, we're working on the standard form, divide by 36 to get 1 on one side. So divide by 36 here to get 1 on one side. So I get x squared over 4 plus y squared over 1, because you want to know the denominators when you're, and z squared over 9 equals 1. Okay, so we have done a lovely job at getting it in standard form and recognizing what it is. Now, when I think about the range, that's, I'm going to think about it real quick, and then I'm going to think about the domain. You could think about either first, it doesn't matter. Okay, I'll think about the domain. Sorry for saying I was going to think about the range first. If I think about the domain, then I know that 36 minus 9x squared minus 36y squared has to be greater than or equal to 0. And then if I get the 36 on the other side, negative 9x squared minus 36y squared is greater than or equal to negative 36. And then multiplying through by negative 1 gives me 9x squared plus 36y squared is less than or equal to 36. And here's where I'm like, okay, this is an ellipse, right? And it's the values that are in the domain are inside of the ellipse. And so here we have this ellipse, x squared over 4 plus y squared less than or equal to 1. So that's kind of our domain. It's the elements of so this is an ellipse. This thing right here, where did I start recognizing it? Right here, an ellipsoid. Right? Now, if I think about the range, remember the range is z equals, right? We have z equals 1/2 of this. So what's the smallest it could be? Well, if the square root could be, the smallest a square root could be is 0. And so 1/2 times 0 is 0. So the smallest this could be is 0. What's the largest it could be? Well, if this was 0, because it would take, I mean, the largest it would be is if x was 0 and y was 0, so that it wouldn't, because because x squared, that's always positive, times this negative means I would always be subtracting from 36. So the largest it could be is if x was 0 and y was 0. So that would be the square root of 36, which is 6, and half of that is 3. So the very highest it could go would be 3. So if I start trying to draw this thing, this is just the top half of the egg, right? The z's go from 0 to 3. And so the z doesn't go all of the way. And this is the domain. These are the values for x and y as what they are. So if I go to draw this myself, and I have over here the drawing, just in case mine's not as beautiful as my unconfidence, So I'm going to go in the x direction 2 and negative 2, because the square root of 4 is 2. And in the y direction, 1 and -1. This is z is 0, is where that's at. Okay, and then I'm going to draw the rest of the egg in. And normally, I would say, well, I'm going to put these together, and I'm going to have, you know, uh, the pieces going, from the ellipse, the the ellipse going from x is 2 and -2, and y is z is 3 and -3. But I'm not going to go to -3. I'm just going down to 0 because of my range. So I'm going to go up here 3, 1, 2, 3, and then I'm just going to kind of um, piece these in the best I can. There's this one, and then this one. And so it's just the top half of an egg is what it is, looking thing. And so there's a picture of it, and you can that one, this one, uh mine's just as beautiful. No one say mine's not beautiful. And I love that it has this so that you can really see that it's flat across the bottom. It's easier to see that definitely on their picture than it is on mine. Go and put that on the 3D grapher if you want to check it out and see how you do. That's the end of page 7. And I hope I push record. Um, that would be just like me not to have done that. Okay, so different story. These are level curves. Um, and a lot of maps, you see maps that are level curves. Let's see, I think they're called contour maps, is what I think they're called. Um, so the shape we get, so level curves are the shape, the shape we get when a plane, and so this is being sliced, a plane intersects our surface. Um, different levels, at different levels. So slice, slice, slice along the axis of the dependent variable, in this case, the z-axis. Is dependent ENT? The map of level curves is called a contour plot. I heard it called a contour map. I don't know, just a little filling in the blank. Professor Leonard, he filled in the blanks, so I filled in the blanks right with him. Basic idea is to set the dependent variable to a constant and sketch the family of curves. That's the idea of how you do it. And so we're gonna give a try to that. And so when they do that, our book calls that value, well, does our book call it K, or did Professor Leonard call it K and our book called it C? It doesn't matter. They call this, instead of calling it Z, they call it like a value K, because they're going to put in a different values of K. And so, for example, we could say that K equals y minus x squared minus 1. And then we could, how did I, oh, this is a different problem than what I had last semester. So I was looking at it and I'm thinking, what the heck? Um, where did the square root go to? Because this problem doesn't have a square root in it. Sorry about that. So my brain got a little crazy, a little cuckoo. Let's pick some values of k and see what this is going to look like. So if k, this is if k equals 0, then this would be 0 equals y minus x squared minus 1. And if I kind of rearrange this a little bit, would you guys agree with me that I could put the y on the other side of the equation, multiply everything through by a -1? So this would look like, I don't know, I'm going to put it like this, negative y squared equals negative x squared minus 1. I don't want to lose it, but I don't want to take up a bunch of room from that. So I'm going to multiply, everything's negative, so I'm going to multiply everything by a negative 1. So did I put y squared? I did. When I moved that over, there should have been y. So negative y equals negative x squared minus 1, right? And then I'm going to multiply through by a negative 1. And when I do, I get y equals x squared plus 1. And I know what that looks like. That looks like a parabola. And I can draw that parabola. Oh, how am I going to do this with my room? What was my plan? Maybe to put it over here? So this is going to be my level curves. So y equals x squared, and I'm just going to sketch it, plus 1 is right here. There's the y-axis. Here's the x-axis. And this level curve that I've just drawn from here, and it's just a sketch, is for k equals 0. And then I want to maybe do one for k equals 1. So I get 1 equals y minus x squared minus 1. And then if I rearrange this, you might be saying, why don't you rearrange it in general? Wouldn't that be fun? Maybe I'll add that to the other side and add that to the other side. So that would be y equals x squared plus 2. Do you guys agree? For k is 1. So this would be up here at a height of 2. And I'm going to try to draw this parabola in. It should be the same width. And so this is k equals 1. So I've drawn 2 values of k so far. If k was, and it would be okay for k to be negative 1, if it was, this would look like negative 1 equals y minus x squared minus 1. And if I added those things to the other side, I would get y equals x squared. Negative 1, and if I add 1 to both sides, then I get 0. And so that would be this one right here. And this is k equals negative 1. And so far, I've drawn 3 of them, and I could draw more of them. I could draw them for k is half, for k is 0.4. There's infinitely many of them, but I'm only drawing a few of them. And it didn't tell me how many. It said sketch level curves for a few values of k. A couple is 2. A few could be 3. And I've done 3. And you could see that I could do more of them. And then I just wanted to let you look at the picture of the surface and imagine if we started slicing on the z-axis. So if we started making slices along the z-axis, we would definitely get parabolas, right? And so here's the parabolas that we would definitely get. Okay, so we did a lovely job at that. That was 6, 7, and 8. Wow, we're doing pretty good, and I have hardly eaten any of my orange. Maybe I'll have another of them. They're so good. Really good. Better than the M&Ms. I can definitely say that for sure. Okay, so we want to look at this one and sketch a few of these. Last semester I only sketched one of them, having too many examples some places and not enough examples other places. So here, if I have k equals the square root of 16 minus x squared minus y squared, and some values that I might let k equal, like k equals 0. So this would be 0 equals square root of 16 minus x squared minus y squared. And I'd like to draw that is what I'd like to do. And so I could square both sides, and then I'm going to square both sides in general. on the original there, but I just wanted to show you, hey, I can just plug this in. And when I square both sides, do you guys agree? And I manipulate it. We've done this often enough on this that I'm going to get x squared plus y squared equals 16. Do you guys agree? I hope you do. If I square and then manipulate it around, and that's a circle is what that is. So here's y and here's x, radius 4. So there's one circle right there. And so I'm just gonna ask you guys this. Would it be okay for me to pick k to be any negative value? And so before I said, oh yeah, I could pick k to be a negative value, and I could definitely on that other one, but it wouldn't be appropriate on this one because square root is always equal to a positive value. So I could pick k as 1, and I said I was going to square it in general, and then here I haven't done it in general, but sorry, that's just the way I'm rolling today. You could do it in general. Squaring both sides, I get 1 equals 16 minus x squared minus y squared. Putting that stuff on this side, I get x squared plus y squared equals 15. And so this is a circle with radius square root of 15, right? This one was for k equaled 0. And put that on here. Square root of 15 is around 3.8. So that's right here, right here, right here, right here. This is a circle. K equals 1. It said a few. I'm taking that to be 3. My notes, I actually drew 3. I was going to say I drew 4, but I didn't. Let me see if I could do the math here. If I squared that, don't do it in your head. Is that what you're saying? I notice that when people do things in their head, they make a mistake. And so yeah, I sometimes do things in my head and I sometimes make a mistake. So here, and then I say to myself, what the heck? 12, is that right? 16 take away 4 is 12, maybe? 16 take away 4. Doing that on my calculator. You know, I'm tired when I'm doing that on my calculator. So the radius, that was the square root of 15 for that one. The radius for this one is the square root of 12. And that was around 3.8. Just for my drawing pleasure, if anyone asked me what the radius was, I'd say the square root of 15. This one is around 3.5. So this is just for my drawing pleasure. Oh my gosh, I almost did that other one, 3.5. That got really bad. So there's k equals 2. But anyway, you get the idea, and you could definitely draw that very well if you did that on a graphing device. And if you think about slicing this, slice, what are you getting? Circles. What is the biggest circle? Well, it has radius 4. Radius 4, yeah, radius 4. And then they're getting, as I slice, they're getting smaller. And so definitely. Okay, so we did a lovely job at looking at those. Not too bad at all. Here's some animations of those, and you can definitely go and look at those animations. So I need to, in order to do them, so if you want to do them on your own, you definitely can. So I got to get my mouse going for computer screen. So there's the computer screen, and I wanted that first animated figure. So this is the first animated figure, and you can animate it, and it just kind of shows you how the level curves go up in there if you kind of slice them, and so it kind of just gives you that idea, and you can move it around if you like, and to get different views of it, looking straight down on it, if I can, and whatnot. Then the other one shows a different figure and the level curves that would go with it, and they're drawing the level curves over here, and you can see the plane um, intersecting with the surface, and then the level curves that are drawn from that you would have. And of course, if you were drawing a map of the level curves, you would leave all of them on there. And this is not leaving all of them on there. It's just showing you the one at a time. Anyway, I think it's kind of interesting. They have other things, that they have videos that you could watch there, and other things if you wanted to look at when would I use this. And so whatever, if you'd like to look at it, you definitely can. How do I go back? So I go over here and I go back to pay-per-view. So we looked at those two, and you definitely are free to look at those as well. Page 9, I should eat another bite of orange. There's only 11, so we're getting there. And this right here, yes, my stomach is growling, but I'm not hungry. So just something to notice here, that as the bowl, this figure right here, and you can go and you could graph this on a 3D grapher, kind of looks to me like a bowl, almost like one of those potato chips things that my brother had at a Super Bowl party. Anyway, but as you go up the sides, uh, it's getting steeper and steeper. And if you look at the level curves, that as you go, um, and your values of as your values of k, these are kind of, I don't know if you guys notice, they're getting closer together. And that's what happens when things get steeper, is that they get just a little closer together. So as the bowl gets steeper, the level curves are closer together. So that's all the point of that was there, or the contours. And then this was a problem right out of your book. And it says the terrain is steeper when, and then I just wanted to make sure that everyone was really on page with that, when the level curves are closer together. And then looking at this, and this came right out of your book. So this is Lonesome Mountain, and here's A, and here's B, and they want us to say where it would be the steepest terrain. And so, well, the level curves are really close together over here, so it would be the steepest, compared to over here, the level curves are not as close together. Okay, so we did a lovely job at looking at that. And so that was page 9 and 10 and 11, and then that's all there is of this. And so they want to know too many examples, I know. So this is a saddle. And this is the contour map that goes with it, or the level curve map that goes with it. And they want to know, when is it the steepest? So when I'm looking on it to see where it's the steepest, well, it's steepest up here, right? And here it's steeper. And then we're just looking at one of these corners, and you could kind of see that as you go in here, it's not as steep. It's like a saddle, like you could sit on it. It's not as steep. So that's that area, not as steep. And then this is the region that's kind of coming up here, maybe on that one. And it's much steeper. So which region of the graph is steeper? So this is the steepest there. And then last but not least, This is example 11. That was example 10. Example 11. If F has the following contour map, so we have this contour map, find the value of 2, 3. So we're going to go here, over 2, up 3. And the value there is at 4. That means the height, if you were to, this is the XY plane where Z is 0. But if we were to graph this would be at a height of 4. And everywhere around the circle would be a height of 4. And then here would be a height of 6. And so that kind of makes me think this thing is mounding up, because we got height of 8. So height of 4, height of 6, height of 8 is what mounding up. 4, 6, and 8. This thing is like that, right? It's like that. It's a cup. That's what it is. It's lower here and then higher on the sides, going up. Why did I say that? I don't know. -2, 3, 1, 2, 3. And that one's not perfect. So you kind of have to sort of estimate that it's between 6 and 8. And it looks a little bit closer to 8. So this one is between a height of 6 and 8, closer to 8. I'm not even going to make a guess, 7.8 or whatever have you. It would just be silly for me to do that. But anyway, so there we've done that. And that's kind of our stories. And so that is the end of 14.1. Oh, how do I turn it off? Oh, I can eat my orange. Oh, bye.